Hello, my name is Jonathan Vada, and I'm part of Group 8 along with Oris Granger, Cornelius Jones, Gabriel Graham, and Alejandro Gonzalez. Our group project was over pressure hazards. Um, I'm going to talk about pressure hazards, their effects, and ways to prevent them. So what we're going to be talking about, we're going to define the term pressure hazards. We're going to list and explain the sources of pressure hazards. We're going to explain the pressure hazards relating to boilers. We're going to summarize the hazards of high temperature water. We're going to describe the hazards of unified pressure vessels. We're going to explain the hazards of cracking in pressure vessels. We're going to describe how to conduct non-destructive testing in pressure vessels. We're going to summarize pressure hazards to human beings. We're going to explain decompression procedures. We're going to go over how to measure pressure hazards, summarizing the methods for reducing pressure hazards, and we're also going to summarize the main elements of OSHA's guidelines for pressure vessel safety. What is pressure? Pressure is defined in physics as the force exerted against an opposing fluid or thrust distributed over a surface. This may be expressed in force or weight per unit area. What is a hazard? A hazard is a condition with the potential of causing injury to personnel, damage to equipment or structures, loss of material, or lessening of the ability to perform a prescribed function. So what's a pressure hazard? A pressure hazard is a hazard caused by a dangerous condition involving pressure. Critical injury and damage can occur with relatively little pressure. The Occupational Safety and Health Administration, or OSHA, defines high pressure cylinders as those designated with a service pressure of 900 psi or greater. I have a quick video that's going to go, how pressure vessels can be deadly, and what the effects of pressure vessel without the proper safeguards, what they can actually do to a facility.
Hello, I'm Chemical Safety Board Chairman John Bresland with a safety message. Pressure vessels are everywhere throughout industry. From major chemical plants to service stations, they are indispensable to modern life. But without appropriate safeguards, pressure vessels can present lethal hazards. These hazards can occur when the vessels are improperly installed, welded, or modified, or when they lack effective pressure release systems. The Chemical Safety Board has investigated a number of serious, even fatal accidents where pressure vessels failed suddenly and without warning, creating deadly projectiles. My safety message is simple. Pressure vessels store huge amounts of energy, and you must never become complacent about the risks. In March 1998, 4 workers died in a powerful explosion at a Louisiana gas well. The blast occurred when a large process vessel, which was only rated for atmospheric pressure, was inadvertently exposed to gas at a pressure of up to 800 pounds per square inch. The vessel had no release system, and a flawed engineering design allowed workers to mistakenly valve off the only vents. When the vessel failed, 4 men were killed instantly. In April 2003, an explosion blew apart an 8-foot tank used to heat sugar caramel for use as a food coloring. The vessel had not been inspected, certified, or registered for use as a pressure vessel, and it lacked a pressure release system. When the vent line became blocked with caramel, the vessel overpressurized and exploded, killing an operator. It caused a large spill of aqueous ammonia and forced the community to evacuate. Finally, 4 years ago, in December 2004, much of Houston was rocked by the violent explosion of a 50,000-pound pressure vessel at a chemical plant. The CSB investigation found that the vessel had been improperly welded and modified by the company, dramatically reducing its strength. Heavy fragments of the vessel traveled nearly 1,000 feet, and nearby buildings suffered structural damage. Texas is one of just 11 states that do not require companies to follow the pressure vessel code. This code of the American Society of Mechanical Engineers dates back to 1915, and provides fundamental safeguards for pressure vessels, including design, fabrication, welding procedures, and pressure relief. In 2006, the Chemical Safety Board called upon the City of Houston to adopt this code to better protect its citizens and its industrial facilities. Unfortunately, Houston has yet to act on this safety recommendation. Just last summer, a stark reminder of the danger of pressure vessels occurred at another Houston chemical plant. At a facility that makes resin for tires, a veteran supervisor died tragically when a heat exchanger was accidentally overpressurized with ammonia. The explosion followed maintenance work when a valve leading from the exchanger to a pressure release system was left closed. These 4 accidents highlight the dangers from pressure vessels when their hazards are not properly controlled. I call on all states and local governments to adopt the Pressure Vessel Code and related boiler standards. Lives will be saved as a result. I'm John Breslin, Chairman of the Chemical Safety Board. Thank you for watching this safety message.
So now we're going to go over the sources of pressure hazards, poor or insufficient training of employees, design, construction, or installation errors, improper application of equipment, insufficient or improper inspections, insufficient or preventative maintenance, failures or blockage of control or safety devices, and a mechanical breakdown or failure or just human error. I have a video of an actual explosion of a steam boiler. This gives a good example of like the damage that a pressure vessel explosion can have on a facility. So what are some of the pressure hazard prevention for boilers? So OSHA recommends the following daily, weekly, monthly, and yearly accident prevention measures in 29 CFR 1910 subpart H. Daily checks that consist of checking the water to make sure that it is at the proper level, venting the furnace through thoroughly before starting the fire, warm up the boiler using a small fire. When the boiler is operating, check it frequently. As for your weekly checks, at least once every week, test the low water automatic shutdown control and record the results of the test on a tag that is clearly visible. So your monthly checks, at least once every month, test the safety valve and record the results of the test on a tag that is clearly visible. For your yearly checks, the low-level automatic shutdown control mechanism should be either replaced, or completely overhauled and rebuilt. Arrange to have the vendor or a third-party expert test all combustion safeguards, including fuel pressure switches, limit switches, motor starter interlocks, and shutoff valves for the yearly checks. Next things that we're going to be going over are the high temperature water hazards, hazards of unfired pressure vessels, and hazards of high pressure systems. Be over in the next slides. The high temperature water systems, they basically are heated to a very high temperature, but not high enough to produce steam. Some of the hazards with these systems are operator error and human contact with high temperature water can result in serious burns or even death. Um, the improper design. The best designs are simply operator friendly, so they don't, things that are too difficult or require a lot of follow-on training to be able to operate them. Too many automatic controls can deliberate proper operator response to emergencies. So if they're too complicated, it can actually hinder the operation of these high temperature water systems. High temperature water can be used as an economical substitute for steam, for example, in industrial heating systems. Unfired pressure vessels that can create heat internally by various means rather than by external fire. For example, steam jacketed kettles. The potential hazards with these are hazardous interaction between the materials of the vessel and the process material, inability to carry weight and internal pressure of its contents, inability to withstand pressure caused by chemical reaction during processing. So basically, when you have a chemical process that creates energy through the form of heat most of the time, and that heat can create pressure in a vessel. So definitely not for mixing chemicals together with an exothermal reaction. And also inability to withstand accidental or intentional vacuum. Some of the preventative measures that you could take are proper design and construction, working pressure and temperature drain, stress relief, radiography, and continual inspection and periodic testing. A lot of time when you buy these, when a manufacturer decides to purchase a vessel, they have to meet the certain codes. They have to, be built to a certain standard, such as documentation as MTRs, where it's made out of from, the material, radiography testing, PMI testing, all your NDE testing. There's certifications that need to be, that a lot of the customers who buy these vessels want. That way, if they're putting into a situation, they have the documentation to at least prove that, hey, we followed this code, or it was built to this standard. And so, if something was to happen, they have that to prove that they just didn't, check all their boxes. Some of the hazards of high pressure systems. Some of the hazards are leaks, pulsation, vibration, release of high pressure gases. Some of the hazard reducing strategies are using anchored pipe supports, limited the number of joints in the system, using pressure gauges. So a lot of time you can use a gauge pressure transmitter. That overall, a lot of the smart pressure transmitters now can report, send a 4 to 20 milliamp signal back to a DCS or control board for a lot of the chemical plants and oil refineries. And that basically sends signals so the operator doesn't have to go out there and constantly check the gauge, especially if it's a critical system. For non-critical applications, they can just use a standard gauge where, it's analog output, where basically an operator goes out there and sees, where the pressure is at. But these pressure transmitters, you don't need to do that. They can report back the pressure on the system so that the operator has it at his control board, doesn't have to leave the control room. You could place barricades around the system. You can also use remote control and monitoring, as I was talking before, and restricting access. Some of the cracking hazards of pressure vessels. These are considered the most serious hazards in pressure vessels, can lead to a complete rupture or leak. Some of the rupturing hazards include blast effects due to sudden expansion of the vessel, possible injury and damage from fragmentation, leak hazards, suffocation or poisoning depending on the contents of the vessel, explosion and fire, and chemical and thermal burns from contact with the contents of the vessel. So, if it explodes, obviously the material of the vessel could be placed pretty far, even out of the confines of the facility. And that could be bad because if it lands into a neighborhood or anything like that, suspecting kid or passerby might not know what this is, pick it up, and it could hurt them. They could travel pretty far. So especially with an explosion like that. Cracking hazards in pressure vessels. These pressure vessels are used in many different applications, contain many different types of substances, ranging from water to extremely toxic chemicals. Leakage or ruptures occurs along the welded seams, the bolted joints, and the nozzles, as you can see in the picture. Some of the most acceptable pressure vessels to ruptures and leaks are the deaerator vessels. They basically remove non-condensable gases, primarily oxygen, from water used in steam generation. It's used in applications such as power generation, pulp and paper processing, chemical processing, and petroleum refining. The failures include cracks caused by water hammer at welded joints that were not post-weld heat treated, and cracks caused by corrosion fatigue. Then you have amine vessels, and they remove the hydrogen sulfide from petroleum gases such as propane and butane. Also used for removing carbon dioxide, used in petroleum refineries, gas treatment facilities, and chemical plants. The failures include cracks in stress or unrelieved welds. And then you have wet hydrogen sulfide vessels. Basically, any fluid that contains water and hydrogen sulfide is considered a wet hydrogen sulfide. Many of the vessels contain wet hydrogen sulfide are made of steel. Hydrogen is generated when steel is exposed to such a mixture. Failures include cracking, blistering, embrittlement, particularly in high-strength steels. The most susceptible pressure vessels to rupture and leak continued. The ammonia vessels are another one, are typically constructed as spheres or carbon steel. These vessels are used for the containment of ammonia in commercial refrigeration systems and chemical processes. Failures include water and oxygen near content in ammonia can cause carbon steel to crack, particularly near welds. Then you have pulp digester vessels. The process used to remove digest pulp in the manufacture of paper involves the use of a weak solution of sodium hydroxide and sodium sulfide in a temperature range of 110 degrees Celsius to 140 degrees Celsius. In Fahrenheit, it would be 230 degrees Fahrenheit to 284 degrees Fahrenheit. Some of the failures include cracking along welded seams, primarily due to caustic stress corrosion. To prevent these ruptures or leaks, it is necessary to examine the pressure vessels periodically. There are 5 widely used non-destructive methods for testing. You have visual examination, liquid penetration test, magnetic particle test, X-ray radiography, and ultrasonic test. Visual, liquid penetration, and magnetic particle tests can detect only those defects that are either on the surface or near it. These are referred to as your surface test. For radiographic and ultrasonic tests, they can detect problems within the material deep. So these are referred to as volumetric tests. And all these tests are referred to non-destructive testing. Some of the types of non-destructive we went over before, the visual examination, which consists of taking a thorough look at the vessel to detect signs of corrosion, erosion, or hydrogen blistering. Then you have liquid penetration test, which involves placing a specially formulated liquid penetrant over an area and letting it seep in. A developing agent is then applied, which draws out the entrapped penetrant and magnifies the discontinuity. Then you have the magnetic particle test, which consists of disturbances that are detected by applying fine particles of ferromagnetic material to the surface of the vessel. It is limited to vessels made of carbon and low alloy steels. Then you have X-ray radiography. This test amounts to making an X-ray negative of a given portion of the vessel. The process works the same way as those used by a physician dentist. So if you go to the doctor and they need to take an X-ray, same kind of concept, sends X-rays, particle, and it brings back an image. Then you have an ultrasonic test. Requires an electronic system for generating a signal, a transducer system for converting the electrical into mechanical vibrations, and vice versa, and an electronic system for amplifying, processing, and displaying the return signal. Some of the pressure dangers to humans. One, you have anoxia, which refers to the rare case of total lack of oxygen. Then you have hypoxia, which is a condition that occurs when the available oxygen is reduced can occur while ascending to a high altitude or when oxygen in air has been replaced with another gas, which may happen in some industrial situations. When you think of hypoxia, I think of deep sea divers, going to deep depths and having to coming up to the surface. A lot of times when they have to go into a decompression chamber so that they can, the pressure in their body can, come back down, come back to atmospheric. That way, with that problems, if they don't, bubbles can form in their blood, and that cause problems. Most likely death. Then you have altitude sickness, is a form of hypoxia associated with high altitudes. It can cause malaise, shortness of breath, fatigue, euphoria, along with the reduction of powers of reason, judgment, and memory. And then worst of all, you could lose consciousness. And if you lose consciousness, like on top of a mountain in the middle of nowhere, you could possibly die if no one finds you. Trapped gas effect, changes in total pressure with a decrease in pressure. Trapped gases will increase in volume according to Boyle's law. Causes air pockets in ears, sinuses, and chest. What they call the jet travel experiences the most. So traveling in airplanes, you might experience this trapped gas effect. Some of the pressure dangers to humans. You have evolved gas effects. It's associated with the absorption of nitrogen in the body tissue. When breathed, nitrogen can be absorbed into all body tissues in concentrations proportional to the partial pressure of nitrogen in the air. If the nitrogen in body tissue, such as blood, is being absorbed faster than it is being exhaled, bubbles of gas may form in the blood and other tissues. This may cause decompression sickness, which can be painful and occasionally fatal. And you have dysbarism. When the formation of gas bubbles is due to the rapid ambient pressure reduction, major causes include releasing of gases from the blood and the attempted expansion of trapped gas in body tissue. This usually occurs when working under sea level or pressurized containers. Some of the pressure dangers to humans is what they call the creeps. It's caused by bubble formation in the skin, which causes an itchy, crawling, rashy feeling in the skin. Bubbles occurring in the brain, although rare, may cause tingling and numbing. Severe headaches, spasticity of muscles, and in some cases blindness and paralysis. Chokes. The chokes are coughing and choking resulting from bubbles in the respiratory system. Often happens, and severity depends on duration of time untreated. Then you have aseptic necrosis, delayed effect of decompression sickness in the bone. Blood in the capillaries supplying the bone marrow may become blocked with gas bubbles, which could cause a collection of platelets and blood cells to build up in a bone cavity. Some bones may become calcified with severe complications when the bone is involved in a joint. Some of the decompression procedures. Employees who work in an environment that is under constant pressure must undergo decompression procedures before returning to a normal atmosphere. These procedures are planned based on the amount of pressure to which the employee is subjected to and for how long. Deep sea divers, such as the one pictured below, are a great example of personnel who use decompression procedures on a regular basis. The majority of the decompression scenarios will need to occur in two stages. Above is a table or an example that briefly demonstrates how to use a two-stage decompression table. An employee will be working for 4 hours in an environment with a working pressure chamber of 20 pounds per square inch gauge pressure, PSIG. Locate 20 PSIG in 4 working period hours in the table in the picture above. Stage 1 of the decompression will require a reduction in pressure from 20 PSIG to 4 PSIG over a period of 3 minutes at the uniform rate of 0.20 PSIG. Stage 2 of the decompression will require a reduction in pressure from 4 PSIG to 0 PSIG over a period of 40 minutes at the uniform rate of 10 minutes per pound. Thus, the total time for the decompression procedure is 43 minutes. Measurement of pressure hazards. Confirming the point of pressurized gas leakage can be an arduous task. Typically, after a gas has leaked out into the atmosphere to a level of equilibrium with its surrounding area, the symptoms of the leak could disappear. There are several methods that allow employees to detect pressure hazards, which will be listed on the next slide. Ways to detect pressure hazards. By sounds, gas discharge may be indicated by a whistling noise, particularly with highly pressurized gases escaping through small openings. Cloth streamers. Soap solution may be smeared over the vessel surface so that bubbles are formed when gas escapes. Scent may be added to gas so that do not actually have an odor. The odor sometimes smelled in homes that cook or heat with natural gas is not the gas itself, but a scent added to it. Leak detectors that measure pressure, current flow, or radioactivity may result for some types of gases. Corrosion may be the long-term effect of escaping gases. Metal cracking, surface roughening, and general weakening of materials may result from the corrosion. But some of the potential causes of leaks: contamination by dirt can prevent the proper closing of gas valves, threads, gasket, and other closures used to control gas flow. Overpressurization can overstress the gas vessel, preventing gas release. Excessive temperature applied to a dissimilar metal that are joined may cause unequal thermal expansion, loosening the metal-to-metal joint and allowing gas to escape. Then you have operator errors may lead to a hazard gas release from improper closure of valves, inappropriate opening of valves, or overfilling of the vessel. The destructive, non-destructive, and proof pressure leak test. The destructive method of testing destroys the material being checked. Proof pressure generates stresses to gas containers, typically 1.5 to 1.667 times the maximum expected operating pressure for that container. Strain measurements may also be collected to indicate permanent weakening changes to the container material that remain after pressure is released. Non-destructive testing methods do not harm the material being tested. Non-destructive methods may include mixing dye penetrants and magnetic or radioactive particles with the gas and then measuring the flow of the gas. Ultrasonic and X-ray waves are another form of non-destructive testing methods and are often used to characterize materials and detect cracks or other leakage points. And then you have proof pressure test. Tests often call for the pressure to be applied for a specified time and then to be released. Stress and strain tests are then applied to the material. Proof pressure tests may or may not result in the destruction of the container being tested. And you have your examples of destructive, non-destructive, and proof pressures below. Reduction of pressure hazards. The reduction of pressure hazards often requires better maintenance and inspection of equipment that measures or uses high pressure gases. Proper storage of pressurized container reduces many pressure hazards. Pressurized vessels should be stored in locations away from cold or heat sources, including the sun. Cryogenic compounds, those that have been cooled to unusually low temperatures, may boil and burst the container when not kept at the proper temperature. The whipping action of pressurized flexible hoses can also be hazardous. Hoses should always be firmly clamped at the ends when pressurized. Water hammering, negative pressures and vacuums. Water hammering is defined as a shock effect caused by liquid flow suddenly stopping. The shock effect can produce loud noises. The momentum of the liquid is conducted back upstream in a shock wave. Pipe fittings and valves may be damaged by the shock wave. Reduction on this hazard involves using air chambers in the system and avoid the use of quick closing valves. Negative pressures or vacuums are caused by pressures below atmospheric level. Negative pressures may result from hurricanes and tornadoes. Vacuums may cause collapse or close containers. Building code specifications usually allow for a pressure differential. Vessel wall thickness must be designed to sustain the load imposed by the differential in pressure caused by negative pressure. And just a quick did you know facts? Similar to how a tank car implodes, when the pressure inside of the tank is substantially lower than the atmospheric pressure on the outside. On a much larger scale, did you know that a black hole is formed when a star essentially implodes on itself? When a star begins to die, the core stops giving off outward radiant pressure to balance the inward pull of gravity and causes the star to implode on itself, forming a black hole. These are some of the OSHA standards and guidelines for pressure hazards. There's no OSHA standard for pressure hazards. They're somewhat covered in 29 CFR 1910 subpart H, hazardous materials, specifically 1910.101 through 1910.105, 1910.1110, and 1910.111. Subsections 101 through 105 talk about compressed gases in general, specifically acetylene, oxygen, hydrogen, and nitrous oxide. The link below at law.cornell.edu will take you to those subparts. Publication 8-1.5, Guidelines for Pressure Vessel Safety. These provide guidelines for safety and health professionals in reference to pressure vessel design, inspection methods, cracking in pressure vessels, conducting safety assessments, etc. And you have the link to the OSHA.gov website, which talks about these guidelines. Then you have confined spaces in pressure vessels. What is a confined space? A confined space is any workplace that has limited means of entry and exit, and it's large enough for a person to fit in, although it's not designed to be occupied by humans. Installation and maintenance of pressure vessels often involves working in confined spaces. So, to do the proper maintenance of these pressure vessels, you have takes going into a confined space, sending someone in there to do the inspection, clean out the vessel, or whatever needs to be done. And that's a kind of just a normal thing in a chemical plant or oil refinery. In summary, pressure, just to go over it again, pressure is defined in physics as a force exerted against an opposing fluid or solid. Pressure is perceived in relation to the Earth's atmosphere. Barometers are used to measure atmospheric pressure. Boyle's law states that the product of a given pressure in a volume is constant with constant temperature. P1 V1 equals P2 V2 when T is constant. Inspiration is breathing air into the lungs, and expiration occurs when air leaves the lungs. Dalton's law of partial pressure states that in a mixture of ideal gases, the pressure exerted by the mixture is the sum of the pressure exerted by each component gas of the mixture. Pa equals Po plus Pn plus Pels. Several methods are used to detect pressure hazards: sounds, cloth streamers, soap solutions, scents, leak detectors, and visual checks for corrosion or contamination. Detection of pressure hazards include destructive and non-destructive testing. Pressurized cylinders and other vessels should be stored away from cold or heat sources, including the sun. Negative pressures or vacuums are caused by pressures below atmospheric level. These are works cited. We used our book, Occupational Safe and Health for Technologists, and below are my references for the videos. Thank you for listening on our project. I hope you enjoyed it. I hope you guys have a good day.